I just ate it too. I didn't eat it. You can go.
So this is chapter 12, number 47. We have a long, solid cylindrical conductor of radius 3 centimeters. It carries a current of 50 amps distributed uniformly over its cross-section. Plot the magnetic field as a function of the radial distance, little r, from the center of the conductor. That sounds horrific. I don't want to do that. But it's not so bad. So let's draw a cylinder.
I just did a bunch of nonsense here.
There's a cylinder. How much current is inside of that cylinder?
50.
50 amps. Do you want the current going up or down?
Up.
Up, okay. Doesn't matter. 50 amps. And what's the radius of the cylinder?
0.03 meters or 3 centimeters.
Radius is 3 centimeters.
Wait, does it matter if it's in meters or centimeters?
If you're going to plug in numbers and actually going to start solving things, you would want to convert this to 0.03 meters. So just always convert everything to SI is my suggestion. Okay. I need to plot what the magnetic field of this is, both inside and outside of the wire. Yes?
Does it not always matter where the current goes, or is it just because of how specific?
Current, if it doesn't tell you a specific direction, it doesn't matter. You can pick. Okay, so I got this current. It's moving through this wire. I want to know the magnetic field outside of the wire and inside of the wire. What do you want to do first? Inside or outside of the wire?
Inside.
Inside the wire? Okay, so if I'm inside of the wire, what I need to do is, I do this like Gauss's law, but I draw an Amperian surface instead of a Gaussian surface. So I just draw a cylinder that's smaller. Okay, one thing to change, that radius is going to be a capital R, because that's the whole radius. So my Amperian surface, it's another smaller cylinder. It has a radius of little r. And then I write down Ampere's law. What's Ampere's law?
The little thingy
The little thingy.
with the flexing.
So for all my YouTube subscribers, we're going to do the little thingy, just the integral. And this is a path integral of B
DL.
dot DL equals mu naught times I enclosed. So the left-hand side depends on whatever surface you draw. The B is the magnetic field, and if you're using Ampere's law, any of the problems that I'm going to give you, it's just going to be a B. It's going to come out of that integral. So then I have to do what's called the path integral of DL. And that's equal to mu naught times I enclosed. And again, similar to Gauss's law, we had dA. We had a surface integral. So it was always surface area. This is a path integral, which means it's how far it is to go around the outer perimeter or circumference of this cylinder. So for a circle, it's circumference. It's walking all the way around the outer path. If this were my cylinder, and I actually have a cylinder over there. If this is my cylinder, let's say this is my wire, I'm walking from here all the way around it. What is that called? That's the circumference, and how big is the circumference of the cylinder? Equation for circumference. It's 2 pi r. So that surface path integral is going to be B times 2 pi r. Okay, so the left-hand side is always about the Amperian surface. B times 2 pi r, because this was a cylinder. What if it were a square of side S? What's the perimeter of a square of side S?
4S.
4S. What if it's a rectangle? What's the perimeter of this? Let's say this is the height and this is the width. 2h, 2 times the height, plus 2 times the width. 2h plus 2l. So I can give you all sorts of different shapes. It's just the perimeter going around the outer portions of that. Equals mu naught times I enclosed. So like Gauss's law, the hard part is usually figuring out what is I enclosed. How much of the current am I enclosing? Inside of this green cylinder that's inside of this bigger wire. Are there 50 amps inside of there? No, there's 50 amps inside the whole thing. So I need to scale it. I need to decrease the current that's going through this. I need just the current that's going through the middle green thing. It turns out if the current is uniform, so uniform current, the scaling I can use bless you. If the current is uniform, then the current that's enclosed is equal to the area that's enclosed divided by the total area times the total current.
What?
This will work as long as your current is uniformly distributed. I enclosed is equal to the area that's enclosed divided by the total area times the total current. Okay? I see us all kind of squinting, trying to read my doctor handwriting. I should go back and make them take away my PhD so that I have good handwriting again.
No, I just don't know.
I enclosed, ENC, is equal to area enclosed divided by area total times I total. Okay. So I enclosed is the area of that wire. And by area, we mean the surface area. So we don't mean the surface area of the whole cylinder. We mean the cross-sectional area that the current is actually going through. So if I have a wire, something like that, if this is my wire, the part that the current is going through is this circular part. The current is going through this portion, right? Flowing up through. It's not flowing out of the sides, so we don't need to take into account the sides of the cylinder. We just care about the face of the cylinder, the face of the wire. So this is the area we want. What is this area? Circle. What's the area of circle?
Square.
It's just pi r squared. Pi times r squared. Which r? Little r. Divided by area total. What's the total area? Pi r squared big R.
Oh.
Pi times big R squared. And the total current is I, which would be 50 in this particular problem. Okay, so I've got my enclosed current. Now that I know the enclosed current, I can plug it in to my Ampere's law. So I have B times 2 times pi times little r. That was all from the Amperian surface, equals mu naught times the enclosed current, pi times little r squared, divided by pi times big R squared, times I.
Why are there so many variables?
And then I solve this for B, and B is equal to mu naught over 2 pi times little r times pi times r squared over pi times big R squared times I. I can cancel some stuff out. I can get rid of the little r squared, get rid of that square. That cancels with one of the little r's. I can get rid of 2 of the pi's. The why you'd want to get rid of pi, I have no idea. It's delicious. E equals mu naught over 2 pi times little r over big R squared times I. There's my magnetic field if I'm inside of a wire. Really, really useful. Electrical engineers use this all the time. We use this to calculate the current that's going through this thing. That lets me create wireless power. So watch this. Watch this. This is kind of crazy. There's a little light bulb. We'll learn about why this is working next class. But I can calculate how much magnetic field is going inside of here. And if that magnetic field is big enough, it should be able to make the light bulb light up without actually connecting any wires. So this is like wireless power transmission. This is the concept behind. Anybody use wireless phone chargers?
Yes.
That's how it works. You don't want to buy the cheap wireless phone chargers. If you buy the cheap wireless phone chargers, they will mess with your phones. They will screw them up, kind of like that. So we get all sorts of crazy stuff that happens. Watch this. Watch this. It's crazy. What's going to happen when I hit it?
It's gonna hit something.
Do you think I can hit the ceiling?
Yeah.
You think it'll hit the ceiling? Let's take bets. How many think it'll hit the ceiling? Raise your hand if you think it'll hit the ceiling. Oh yeah, let's have some fun.
Oh, Jesus.
Yeah, they'll really smack into it. Anybody want to get shot? See how hard it is? Hard it hits? Yeah? You ready?
You want me to stand up?
I'm not going to shoot a student in class. Are you crazy?
I was like, what is going on?
I might be tenured, but I'm not immune. I'm not crazy. Okay, we'll learn a bit more about why that actually works next class. But we can calculate the magnetic field that's letting that actually happen using this equation. But not just that equation, because we don't want the magnetic field just in the wire. We want the magnetic field that's outside of the wire, outside of this whole thing. We want the magnetic field that this thing is experiencing. Okay, that's causing the repulsion. The magnetic field that makes this actually light up. The magnetic field that takes this, so this is a compass. You have to look at the, trust what this, your classmates are saying up here. Look at the compass. Compass is working just fine. And then I turn this on. What happens to the compass?
It goes towards that.
I control magnetism. I am magneto. Weakest magneto in existence. But we can calculate that magnetic field and how big that magnetic field is outside of the wire. So let's do that now. Here's my coil. Let's shuffle along this mortal coil. There we go. I just did an English class. How much current?
50, right?
50. How big is the wire? 0.03 meters. Got memories of goldfish in here. And I want to know what's B if little r is greater than big R. So now I have a big wire. It's bigger than the whole thing. Okay, so on the left-hand side, I've got integral path of B dot dl equals mu naught times I enclosed. What do I do to the B?
Take it out.
Treat it very carefully because bees are dying out and we need them to pollinate correctly, but we take it out of the integral. So we're being exclusionary of the bee. That's why they're all dying.
Makes sense.
Then we have the path integral of dot dl equals mu naught times I enclosed. The path integral around that circle, what is that? We're going around the exterior of the circle. So what is that equal to? 2 pi r. B times 2 pi r. What r?
Little r.
Little r. Because it's always the surface that you draw to enclose the surface that you're interested in. This is equal to mu naught times I enclosed. How much current is enclosed there? The whole thing. So just plain I. Do I have to scale it at all? Nope. What about all this space from the edge of the coil to the green part? Do I care about that? Does that matter?
No.
Nope. Who cares that that's empty space? We don't care. Doesn't matter. All I care about is how much current is inside of there. And all the current is enclosed. So I don't need to scale anything, and I just get B is equal to mu naught times I over 2 times pi times r. Little r. This is the magnetic field outside of the wire. This is given in books as just a general equation. If you read the headline, the title of what this equation is, it's the magnetic field of a long straight wire. Any wire is going to create that magnetic field. Mu naught times I divided by 2 pi r. Any wire, moving around. And any wire creates that magnetic field. So if I take a compass and I move it near any wire, I can actually detect a tiny, tiny little magnetic field if the magnetic field is if the current is high enough. If I go to an electrical wall outlet, you'll actually see the magnetic field of a compass actually change.
So if you solve for I, not I, sorry. Okay.
So B, you can plug in all the numbers if you wanted, but this problem didn't ask us to do that. This problem asked us to graph this. It wanted a plot. So to make a plot, I need to know what variables I have. I need to plot two things versus each other. What's going to be the y-axis in this plot?
Magnetic field.
Magnetic field. B is the y-axis.
Guess.
Good guess.
And what would the units of that be?
Tesla.
Tesla. Magnetic field has units of Tesla. What would the x-axis be? What variable does the magnetic field depend on?
I,
Anybody know?
R,
We're tossing out variables up at the front. I, R, mu naught, 2, pi. Which one of these are variables? Is mu naught a variable? No, that doesn't change. That's constant, right? How about I? Is that a variable?
no, not here.
How big is I?
50.
They told us the current is 50.
Oh, so it's
What about this? How big is the I in this part, though?
It's more than 50.
Am I enclosing 50 amps in the first part? No. So what's I there?
Less than 50. R over R squared.
I is still 50. I still have the current, but I'm scaling it. That little r divided by big R squared, that's where I'm doing scaling. Okay? So that I is still 50. I is a constant. That's not a variable. How about 2? Does the number 2 change? No, only if you're doing weird, freaky math. No math majors in here, because I stole the one math major for engineering. How about pi? Is pi a variable? Nope. What's the only other variable left?
R.
R. R is the variable. Does R change?
Yes.
Little r is changing depending on if I'm outside or inside of the wire. So little r is my x-axis. So if I look at these, I can do B is proportional to, let me write that so it's not chicken scratch. Proportional to, looks like a Jesus fish without the tail. That means proportional to. B is proportional to R if R is less than big R. And then in the second part, B is not proportional to R. What is B proportional to? How is B related to R in R greater than big R? Thought I heard somebody say inverse. Yeah? B is proportional to 1 over R.
Why?
Why? So we have the question, why is that true?
For the last one.
For this one, I have all these not letters,
Yeah, it's just one.
and I'm left with 1 over R.
Okay.
Right? So it's proportional to 1 over R. So if I plot this, this looks like this. I have proportional to R, all the way up to R is equal to big R. So this would be my radius on my x-axis. What would be my units of my radius?
Meters.
Meters. And then proportional to 1 over R, which looks like this. R is proportional to, B is proportional to R, and then B is proportional to 1 over R. I'm going to ask you to do a plot like this on an exam.
I'm crying.
You will?
No.
Oh.
I
I was about to say. I'm leaving.
But the concepts we've used here, they apply to any kind of Ampere's law problems. Okay. Any questions on this? using the concepts here, you should be able to solve problem number 47. 47 is much more like an exam problem that you might see.
You mean 48?
Or 48. Yeah, 48, because this is 47. So 48 is more like the exam that you'd see. No questions on this? No?
I feel like I have a question, but I don't even know what it is.
Where to start?
You can keep thinking about it. Now, for your in-class problem, because I just solved your in-class problem for you, put down in the comments when you upload your solution if you have any questions on it still. But also, I would like you to solve this. I saw a couple of people asking about the right-hand rule. So I want you to solve this problem. The magnetic field from a long straight wire, but I'm going to do something with that long straight wire. I'm going to take that wire and I'm going to kind of bend a loop into it. And I want you to find what's the magnetic field at the middle of this loop. So I have current that's coming through here. And then I have a loop of wire. That loop has a radius of big R. I want to know what's the magnetic field directly at the middle of this loop. So I've got current coming through, goes up and around, and then it keeps going through. I also want to know, if you ignore the loop and think about being both above and below this long straight wire, what direction is the magnetic field going if I'm up here versus if I'm down here due to this wire? To figure that out, you need to use the second right-hand rule. Second right-hand rule. At this one, there's no kind of X, Y, Z, I, J, K kind of loop that you can draw. You need to use your right hand to do this. Okay? If I want to know what direction the magnetic field is going, due to the direction of the current, I take my thumb and I put it in the direction that the current's going. So my recommendation is to literally do this. Take it, put your thumb in the direction the current's going. My current's going this way. Then I take my fingers and I point them in the direction, point them to the region where I want to know the magnetic field. So, to find the direction of the magnetic field in region 1, where would I point my fingers?
Up.
I point them up. Right? My thumb's going this way. I point my fingers up. So that would point me up towards this region. And what happens when I bend my fingers? There's only one way to bend my fingers. Don't try bending your fingers backwards. Bend them in the natural direction. I have seen students taking exams and doing this. Don't do that. You'll injure yourself. Okay, you bend your fingers the direction they would normally bend. And what direction are my fingers now pointing?
Out of
They are pointing into the board. What direction is that?
K.
Negative K is into the board. So the magnetic field, due to this long straight wire, in region 1 is going into the board. How do I find it for region 2?
You do this?
I check my thumb, point in the direction of I. Fingers, do I want my fingers to point up? No, what do I have to do? I have to have my fingers point. How do I make my hand do that? I rotate it, pop my shoulder out of the joint right before I go on vacation. That'd be great. And then I bend my fingers. What direction are my fingers going? Coming out me. What direction is that? Positive K. So underneath in region 2, the magnetic field is coming out. Okay? Now the hard part is figuring out what direction is the magnetic field going because of this loop. So is it coming out or is it going in? Now what's the magnitude of that? Okay, so that's the other thing to figure out. Okay, so that's what you got for in class. Any questions that you have about the problem I solved? And finish solving this and ask any questions you have about this too. Work together, talk to each other. I'll come around and help too.
What is this in class called, right?
Yes.
Alright.
I'm very lost.
It's okay.
I'm not doing
Save it for next week. Not next week, Wednesday.
Oh god. Don't
Yeah,
say that.
Wednesday's so hard. I like watch the videos just out of curiosity, you know. Just it's like sometimes I skip to do the videos because they help understand the video before. And I was like,
It is